Hey everyone. I'd say good morning, but it's the afternoon. So good afternoon. I'm sorry that today's video is being posted a little bit late. It's been a struggle some days doing homeschool with my kids, especially my 8-year-old daughter. It's been a battle of wills today. She's been very stubborn. Um, But we're going to do this video. We're going to get it up there. Um, Today's video is on mechanical properties of materials. Um, for those of you in the material science program doing the structural materials, this is definitely going to be review. For those that were in Material 680 last quarter, we covered some of this briefly in talking about in our lesson on mechanical testing. So most of this should be at least somewhat familiar. But I wanted, it's in the curriculum here because, well, we'll get to that when we get to the notes. I'm gonna jump over real quick to the syllabus. Here, and just point out, so today, we're doing chapter 6, and this is the first of several lessons dealing with metals. So from now, for the next week and a half about, right, we'll be covering metals, starting with an overview of mechanical properties today, and then dislocation strengthening, which is the primary mechanism for strengthening materials. And then talking about how materials fail, and then moving on to some of the structural portion of helping to understand, okay, structurally, why do different metals have different material properties, mechanical properties, and how they are changed based upon the structure. So we'll be talking about metals here for the next week or so. But today, like I said, we're going to be talking about, just want to make sure that I'm sharing the right window here. Okay. We're talking about mechanical properties of materials, right? The next lesson, or the next few lessons, will be covering, right, how these mechanical properties are produced. But today, we're going to cover how, what properties we're talking about, and how are they typically measured. How can we be assured, and how can we be assured that our measurements are accurate and consistent, and actually measuring a mechanical property of a material as opposed to a property of a particular object. And so we're starting here. Remember, the unifying theme of this course is this processing, structure, properties, performance relationship. So right now we're focusing in on the properties. What are we talking about as far as mechanical properties are concerned? Later on we'll be working our way back, talking about the structure that forms for various metal alloys, and then the processing required to get you to that structure. And so the first thing to talk about when in regards to mechanical properties is this curve here. This is an example of what we call a stress-strain curve, and this is produced by applying a stress to a material sample, right? So that would be the y-axis, and then measuring the response of that sample to that stress in the form of strain. Right? So this is some elongation. And in this test, right, the forces applied are static, meaning they're not changing, or they're very slowly varying. So we're increasing the force applied, increasing the stress of the sample slowly. And this can be done, as we'll see later, in tension, compression, or shear. You can apply the stress in one of a number of ways. But a stress strain is essentially, in all cases, is recording the response of the material mechanically in response to some applied stress. This particular example here is tension, which is probably the most common stress strain curve. And so we have the beginning of the test here at 0 stress, right? And as we apply a stress, right, we're going to get an elongation, and the relationship initially between this elongation or the strain, right, the stretching of the material, is this initial region that has a constant slope, generally, that we call Young's modulus, and this is what we call the elastic region. At some point, the material can't withstand the stress anymore, right? And it starts to be permanently deformed, right? So we're stretching it beyond the point at which it could recover, and you get much larger degrees of strain. And as we'll see later on, right, this strain is not recoverable if you remove the stress, right? So as you're stretching it, you're getting permanent deformation. At some point, a region of the sample will begin to become much thinner. Call this necking, and that continues until you get total failure and your part breaks, or your sample breaks into 2 pieces. And so this stress strain curve is made the way it is because mechanically we want to isolate a material property. So a mechanical load, right, or a force, right, we're talking about in SI units newtons, or English units pounds. So we're applying some force, and a real object is going to withstand a load. And the thicker the cross section, the heavier the part, the more load you'd expect it to be able to withstand. When we're looking at a material property, right, we don't want to think in terms of a load, right, because we would have a different result if we made a different choice for the size and shape of the sample. And so here we want to be careful to divide out the cross-sectional area, and so that it doesn't really matter what the size of our sample is, we can achieve the same stress within that material that we're measuring the mechanical properties of, right? So we're not applying a force, we're applying a stress, right? That would be units not of newtons, but of newtons per area, newtons per square meter, or Pascal, right? So that would be a unit of pressure. The English equivalent would be pounds per square inch. So we're applying some force over an area, right? That gives us sigma, or the stress component of our stress strain curve. And then for the strain, right, epsilon, here we don't want our measurement to be dependent on our choice of length for our sample, right? You can imagine that a longer sample to begin with will be able to stretch more. Absolutely, as opposed to a relative sense. But we want to make sure that we're isolating the strain of an arbitrary sized piece of material, so that the geometry of our sample, again, is not included in our results. So here, the strain is not delta L, how much we stretch, but it's delta L relative to the overall length, right? So it's some percent of the overall that we are elongating. And that gives us the strain, or the other part of our of our stress strain curve. And so when you're doing tensile testing, right, it's typical that you would make a sample, right, shaped something like this, where you have thicker ends that are either held in hydraulic grips or have threads cut into them so that they can be threaded into the tensile testing machine. And so those ends are thicker and heavier than the middle section. The idea is that you want to control where the sample will elongate, deform, and ultimately fail within a section that you can measure the strain during that process. So you're going to make this section, what we call the gauge section, thinner to confine the deformation there, because a thinner cross section is going to resist a lower force. And so if you apply the same force along the whole sample, the stress is going to be highest here where the cross-sectional area is the thinnest. You also want to make sure that your gauge section here is long enough that you can achieve a uniform force across the cross-section. And this is called St. Venant's principle. And what it says is that the further away from the end you get, the more homogeneous the force is across the cross-section. Right? You can imagine if you had these threads cut into the outside of the rod, right, the force would be transmitted through the contact surface of those threads and wouldn't necessarily be uniform right at the end of this gauge section. Right? But as you move away from that irregularity, St. Venant's principle holds that the force along the cross-section becomes more uniform, right? And so you want to make the gauge section of a reasonable length and then measure the strain towards the center of that, because then you'll be in a more uniform force scenario. But tensile testing, these stress strain curves are typically generated through some sort of a test machine, something like this. This is using screws to generate the force. The exact manner can vary from machine to machine, but generally what is done is the distance, right, between the moving and stationary arm of the load cell is increased at a constant rate. So we're actually forcing a constant rate of elongation, and then we're measuring the force with this load cell so that we can generate points in our curve that are of stress and strain. But instead of ramping up the force and measuring the elongation, it actually goes the other way. So it's easiest to start talking about tensile testing, mechanical testing, but let's not forget that we can apply a load or stress to a sample in a number of ways. The first alternative would be in compression. So you can, instead of having the pulling force, you can just have a pushing force where you are compressing the sample rather than putting it under tension. And here you can think about, in some cases, the stress strain curve looking similar, just sort of being inverted through the origin. So I would apply a negative stress pointed in the opposite direction, and I would get initially, right, a linear deformation, but instead of being an elongation, right, it would be a contraction of sorts. And then you would get a similar yielding in compression where you would, instead of getting necking, you might have more of a pancaking kind of deformation, especially for ductile materials, which is kind of illustrated here, right? So you can still get the delta L over L. It would just, instead of being an elongation, it would be a contraction. So you can have compression. Also, You can also deform materials in shear and in torsion. So in shear, instead of having a force applied that tends to pull the atoms apart, here we're applying sort of opposite forces, opposite directions that provide a sliding motion between the atoms of our sample. And so these opposite forces will tend to produce a deformation that looks something like this, where instead of getting an elongation, we're getting some sort of an angle deformation where we are kind of bending the sample in some angle. And so this is the analog of strain, this delta, and instead of some angle. And like we saw before, right, there is a proportionality constant between the shear stress that we apply and the deformation that we observe, right? So here we call it G as opposed to Young's modulus, but the idea is very similar. And we can also, instead of having a shear component like this, we could put the sample under torsion, where we are twisting it about an axis of rotation, and again measuring this angle of deformation in regards to some applied torque. Okay. And so within the sample, in any case, when we do a stress strain or mechanical test, we are producing some sort of state of stress. And in simple terms, right, we can think about the stress sort of in this uniform perpendicular cross-section here as just being the cross-sectional area. But there are other ways that we could slice the material and ask the question, okay, what is the state of stress on an arbitrary slice through this cross-section? And when you do so, right, you have two components of stress. You do have the one that goes parallel to your axis. Well, you would have within that state of stress, right? You would have two dimensions along that plane, and you can define them mathematically in terms of the overall stress applied to the ends of the sample, right? Ultimately, that's what we're talking about. And these mathematical relationships reduce to our normal kind of our initial look where we're looking at just the cross-section if we think about the plane with an angle relative to the cross-section of 0, right? So we'd have the cosine of, well, the cosine of 2 pi. Well, if you put in 0, right, you get cosine of 0 is 1, plus 1 gives you 2, 2 over 2 is 1, so this just reduces to the simple picture at the in the 0 degree cross-sectional plane. And the sine of 0 is 0, right? So there's, in this cross-section, it's all tensile and hard and no shear. But as you increase the angle and look at different planes, not this perpendicular cross-section, the state of stress on that plane is going to have some component of shear. And so you have this complex stress state in off-angle planes. And what you'll see is that the yielding, right, so if you increase the applied stress to the point where you go beyond the elastic region, right, and we'll talk about this a little bit later on, a little bit more, you start to get plastic deformation, right, where the atoms of your sample rearrange as opposed to increase the distance between the bonded atoms. And it is going to rearrange first where the applied stress has overcome the ability of the material to resist it. And if you look at this table here, right, you can see for most, or at least all materials in this table, and all materials generally, the shear modulus is about a third or so of the Young's modulus. And so the ability to resist tensile forces is generally several times greater than the ability to resist shear forces. And so as the angle on these planes increase, right, at some point, even though you have not overcome the tensile properties of the material, right, you could reach the limit in shear, in which case you would get sliding on some of these off-angle planes. And we'll see when we talk about dislocation motion in our next lecture that single crystal samples, you actually get yielding along these planes and kind of a stair-step pattern of yielding as this crystal deforms, right? So, so it's in response to reaching the limit of shear first, right? But the big point there is that you have complex state of stress within the material. Okay. And so, what do we actually, to try to tie what we were talking about last week to today's material? Recall when we form an atomic bond, right? We have this balance between the attractive force of the Coulombic attractive force between charged particles and the repulsive force of electron overlap as they get close enough. And there's a balancing here where the attraction and the repulsion, right, are in balance, and the net force would be zero. And so, right, we're talking about force in this scenario, and when we look at a stress-strain curve, we're also talking about force in the stress. We have force per area. And so what's the link between these two, right? Well, when you apply a stress to a material, right, what you're doing is you're pulling on all of these atoms that are bonded by these attractive forces here, right, and held in place also by the repulsive force. And so when I pull on these, right, how much do they stretch? Well, it depends on the strength of the attractive force that's holding them together, right? So if I have a strong attractive force, generally that is going to correspond to having a steep slope here, right? Because if this attractive force, right, is ramping up very quickly here, then it's going to force the repulsive force to ramp up quickly here. So I get a rapid change in the force in this region about the equilibrium point, right? So if I then come in and apply a macroscopic force that gets distributed amongst all of the atoms, right, what I'm doing is I'm elongating each atomic bond slightly, right? And so the strength of these attractive forces is going to be reflected in the slope of this curve here, which is analogous to the Young's modulus, right? So here what I'm doing is I'm applying a force and measuring a change in R, right? This is the atomic version of strain. What I'm applying here is applying a force and measuring elongation, right? So it's kind of a macroscopic. So if I were to add up all of the teeny tiny changes in interatomic spacings here, I would get, right, the overall strain. And then if I compare two materials, right, one that's weakly bonded, one that's strongly bonded, right, I should see, I would expect to see a change in slope here, and have a steeper slope for the strongly bonded and a shallower slope for the more weakly bonded. And this is only applying to the elastic region of a stress-strain curve, right? So these force curves apply to one atomic bond. And so if I were to pull, and change the arrangement of these atomic bonds, then I would maybe have a different force curve, right? So this is just the elastic region. It would just be this first part of the stress-strain curve where I start at a 0 stress, I apply a stress and see a corresponding strain, the slope of which, again, is the Young's modulus, or the modulus of the elasticity. And so if I unload, right, I should go back to where I began. That would be this analogous, right, to just kind of going a bit up this slope and then coming back down. This may not, so for metals, this happens very rapidly, right? So it's tempting to think that, oh, this is an instantaneous change. It's not. For metals, it's just low. It's significant for other classes of materials, though, that we will see later on, especially for polymers, right? If you've ever stretched your rubber band, right, and then let it go, right, it takes a few seconds for it to go back to its original length. It's not instantaneous. Okay, so let's apply this idea to some other phenomena. I want to try to make this connection between what's happening at an atomic level and the material we talked about last week to the mechanical properties. So a relatively minor point in Callister was that the modulus of a material generally has a temperature dependence, right? It's not drastic, but it's significant. So for instance here we see that steel, from say liquid nitrogen temperatures up to a couple hundred C, right, we might see a decrease maybe by a third in the Young's modulus, which is, significant but not outrageous. And so if we think back to our bonding picture, right, these sort of ideas here with these repulsive and attractive forces and these force curves, does this plot of temperature dependence make sense? Well, if you think about the potential energy, right, so if I take this force curve and I integrate, right, I get energy. So whereas here the force is 0 at the equilibrium distance, for the energy, right, I would have a I forget if it's integrate or take the derivative now. But in any case, at the equilibrium, I get a minimum in energy, right? And so I have a bond that, on average, is at this equilibrium spacing. But remember, I have random thermal energy in my material as long as I'm above absolute 0. And so what I have instead is a bond, right, that is constantly vibrating. And so the atoms are moving about this equilibrium spacing, but it's oscillating from being a little bit closer to being a little bit further away, right, back and forth. As I increase temperature, I go further up these sides of this curve, right? Eventually, I have so much oscillation that I can break the bond entirely. That's what happens when we go from a solid to a molten material. But if I'm not going up that high in temperature, right, why would I see a change in the Young's modulus? Well, we think about this oscillation as being a simple harmonic oscillator, meaning that it's kind of a ball and spring model, but that's only really true right down here, right? And even then it's an approximation, because the real force curve is asymmetric, which means that as I oscillate more extremely about this equilibrium spacing, I actually spend more time, right, further apart. than I do closer together, right? So I see an average increase in the bond length as I go up in temperature, right? So that would explain why we see generally expansion of metals with higher temperature, right? Because I spend more time at a longer bond length than I do at a shorter bond length, so I get an overall increase in bond length over as I increase temperature. But as far as Young's modulus is concerned, right, if we come and look at this picture of force here, you know, pick any particular material here, right? So I have this force curve, say for the red material, and at the equilibrium spacing, I have a certain slope. Remember, the slope is the same as the Young's modulus, right? It's how much separation do I get between atoms for a given amount of force. Well, if I increase the temperature and I shift that equilibrium spacing slightly to the right, to longer separations, now I'm looking at the slope not here at 0, but actually a bit further out, right? And you can see here as I'm increasing separation, my slope is actually slightly decreasing as I go up this curve, which tracks with this slight decrease as I go up in temperature. So again, you can make this connection between the properties of the atomic bond and the force curve at an atomic level and the mechanical properties that we observe here, especially in the elastic region where we're looking at the elongation of individual atomic bonds and not yet looking at the rearranging of large groups of atoms that we see later on when we talk about deformation. So I'll also mention here Poisson's ratio. This was listed in this table up here, and it's about 0.3 or so. And this idea is essentially that in a material, mass is conserved, right? So if we're going to pull and elongate in one direction, right? If we're getting longer in one direction, we have the same amount of material, so it must be getting smaller in the other directions, right? So as there's a relationship, and the ratio between the elongation in z and the contraction in x and y is what we're talking about with Poisson's ratio. And so you can see here, right, that it's about 0.3 for most of these metal materials. And it's fairly consistent among widely varying metals, and so this allows us to use Poisson's ratio, which is generally 0.3 to 0.4, and define a relationship between the Young's modulus and the shear modulus, because it's these shear forces that are pulling the material inward as I elongate in one direction. Okay, so that's enough on the elastic region. So what happens if I continue to increase the stress of my material? Well, at some point, right, I've stretched the bonds as far as they can go, and I have, at least on one plane in my material, I have reached the limit of the ability of the material to withstand tensile and shear forces. And so what happens is that the atoms begin to rearrange. They don't completely pull apart. I don't break all of the atomic bonds in a particular cross-section at the same time. I mean, that would actually take an enormous amount of force, and we're just going to, what we say, slip, right? So we start to break bonds, and the atoms start to shift in relation to one another and move into new positions, right? Those new positions corresponding to a material that is slightly longer than it was before. And so that reduces, could reduce the stress. And as we'll see later on when we talk about strengthening mechanisms, oftentimes that slip will actually increase the strength of the material. And we'll talk about why that happens in later lectures. But as we break these bonds, right, we're getting permanent deformation and a permanent change of the structure of the atomic structure. In metals, we call that a slip or dislocation motion. For non-crystalline materials, right, we refer to this as viscous flow. But the beginning of this deformation, right, is sort of the interface or the transition between the elastic region, where if I remove the stress, right, I'll go back to where I started, and the plastic region, where I don't go back, right? I might recover the elastic, but I have this permanent deformation that will always be there, right? I have permanently deformed my sample or my part, and but the exact transition between elastic and plastic is not always immediately apparent, even for materials like this nominal stress strain curve that I showed earlier. Where there's a defined region where clearly it begins to yield. It's still difficult to say, did it happen here or here? Where in this region did it exactly happen? And so we determine the point of yield not so much by looking at where does the curve change, which can be subjective. Instead, we have all agreed on a particular convention, right? So a common one is 0.2% offset. So when you're measuring the point at which plastic deformation occurs or begins to occur, that's what we call the yield strength, and that is defined by going to a 0.002 strain, right? That's 0.2%, and then drawing an imaginary line here at the same slope as your elastic modulus. Right, so you're going up at the same slope. At some point, right, your imaginary line will intersect with your data. Right, at that point, that's what we call the yield stress or the yield strength. Right, based upon this 0.2% offset. That's one option. Right, depending on the material, you might also just say a preset strain level. Right, so you say, okay, whatever the stress level is at some, I don't know, 0.5% strain, whatever it is. Or perhaps you're working with a material system where you really do see a very defined yield point, in which case you can just pick that. But this yield strength, right, this is typically what's used as the design strength, right? You typically don't want to design something that will deform, right? So this limit, where the material will start to yield, is sort of a hard stop, right? You can't design it to withstand any more stress than that, because it will only be able to do it that one time, and then it will be permanently deformed. Generally, that's undesirable for mechanical design. And assuming that you're going to get plastic deformation, right, there are more material properties to describe the ability to plastically deform, one of which is ductility. And I mentioned it before, and we'll see it later when we talk about dislocation motion, and with the processing of metals in general, that you generally get a trade-off between strength and ductility. And it's due to the fact that they have the same root cause. Both are caused by the degree with which dislocations can move. Right? We'll see this much more in the next lecture. Right? But if dislocations can move, then you get lots of yielding, and the material is very ductile. Right? If they can't move, then it takes a lot of stress to make them move, and that's corresponding to a very strong material. But if they can't move, then they're not very ductile. So the strength and ductility is very much kind of a zero-sum trade-off, in the sense that if you increase one, you decrease the other. But it also is the source of much of the design or the material flexibility of metals as a class of materials, that you can tailor the strength and the ductility across a wide range to get the material properties that you would want. And so we can think about ductility as a material property, and it's generally expressed either in terms of percent elongation, where we're looking at the strain as a percentage, or the percent reduction in area, where we're looking at how much the cross section can be reduced before failure in terms of a percentage. And so if you look at the stress strain curve, you can almost immediately distinguish a brittle material from a ductile material. Ductility refers to lots of plastic deformation, right? So you should see a very wide range of strains after the onset of plastic deformation, right? So a ductile material will stretch, right, for a long time before fracture, right? As opposed to a brittle material where you have the elastic region, very little deformation, and then fracture. And so some degree of ductility, right, is generally desirable, even if you need to trade off a little bit of strength to get it. This is referred to as resilience, right? So as I'm yielding, right, moving those atoms around takes energy. And the amount of energy that it takes, right, is represented by the area under this curve, right, which is what we refer to as resilient. So if I want to have a very highly resilient material, right, that's going to be a combination of a high yield strength, right, which forces the kind of the height of this area to be large as I increase in stress before the onset of plastic deformation, and then I want to have as much ductility after that point as possible, right? So it's very much an optimization problem to maximize the resilience. But you can think of this kind of as resilient because you might have a material that deforms, right? So it kind of gets knocked down a bit. But it doesn't give up, right? It continues to support the load even if it needs to be stretched and bent and deformed out of its, right? It doesn't just immediately give up and break, right? So you can kind of, I guess, make a connection there between, resilience in people and resilience to materials, right? You can knock them down, but they don't give up. And along the same vein, right, you can talk about toughness, right? So if we're thinking about the resistance to fracture, right, a tough material is going to be something that deforms at the edge of a crack as opposed to fracturing. And this comes from combination, again, of strength and ductility, just like resilience. It's generally measured more narrowly in terms of the elastic region, right, where we're looking at the area just in this elastic region. So we want to maximize the yield strength, right, and actually minimize the elastic modulus so that we can get this area to be as high as possible. Okay. Now that we've talked a little bit, or quite a bit about stress-strain curves, right, now we'll kind of, I guess, pull back the curtain a little bit and say, well, that actually this stress-strain curve that we showed before isn't correct. Right? Remember that when we are applying a stress, right, that's force per area. Well, what happens to this area as we start to elongate? Well, right, we are getting stretching, and as it stretches, that material is being pulled from somewhere, right? So when it's getting longer, it's also getting thinner. And if the cross-sectional area, if it's getting thinner, then the cross-sectional area must be going down. And so if it's going down, right, this stress value is not actually the same as it was, right, because the force is being applied over a smaller area. And so when we look at the stress strain curve, you might be tempted to think, well, look at that. After necking, it actually got weaker. Well, that's not the case, right? If I use the same area, then it looks like it got weaker because it's able to resist less force. But that stress is actually much higher because that force is applied over a much smaller area. And so the difference here, what we were looking at in this figure, is what we call engineering stress, right? Where it's more convenient to just use a constant cross-sectional area, even if it makes the curve bend down. But it's not true. So to go from engineering stress to true stress and strain, right, we need to account for this cross-sectional area reduction. And we can make an approximation with using these expressions here, where we have this correction accounting for the strain, right? So as we strain, we are increasing the stress, right? Because the strain is correlated to a reduction in the cross-sectional area. These expressions here that relate the strain, or the engineering and true stress and strain, is only good up to the necking point. Once we get to the necking point, these expressions are no good, and you actually can't calculate the true engineering stress without some estimate of what the actual cross-sectional area is. And I think there's a homework problem for you guys to play around with that. I think I mentioned this a bit before, but the elastic region, so we've applied stress and we get plastic deformation, but that doesn't mean that the elastic deformation has gone away, and it doesn't until we remove that state of stress. And we will recover, right, the elastic strain. Oh, a bug just flew in my window. We will recover that elastic strain, but that plastic deformation that has occurred is permanent. So it's pretty useful to be able to measure mechanical properties of materials, but it's destructive, right? You have to break the material in order to get any information about its material properties, which I suppose is fine if you are characterizing an entire class of materials or doing materials research. But if you just want to measure a particular part non-destructively, tensile testing is not really the best tool. A much better one is to measure the hardness. And this, in hardness, has some analogy to tensile testing. It's still the resistance to plastic deformation, except instead of looking at plastic deformation of the entire part, you're just looking at a very localized area of plastic deformation. Hardness started off being kind of a gemology tool, where we were looking at the ability of one material to scratch another. But in our sense, what we're actually looking at is plastic deformation, local plastic deformation, and it's usually measured in terms of some penetration depth into a material from an indenter of some type. So we apply force to some indentation probe, and we measure how much it indented into a particular material. And this can be much better, much preferred over tensile testing because it's simple, cheap, fast, non-destructive, and still quite useful because there is a strong correlation between hardness and tensile strength, right? So if I can reduce its ability for the indenter to deform it, right, then I'm also going to reduce the ability for tensile stress to deform the material also. However, it is sensitive to procedure, right? So how I apply the indenter, what the indenter is shaped like, what forces I'm looking at, how close together they are, how close the indenture is to a certain other feature within the material is important. I need to follow those guidelines in order to have good results. And there's several different scales. I'm not going to go into super detail here. Usually they differ on how the load is applied and what the shape of the indenter is, right? So Rockwell and Brunel both use tiny ball bearings as indenters. Knoop and Vickers use a diamond as the indenter. And they all have, right, similar scales. So if you kind of put them all next to one another, you see here's Knoop and Brunel, Rockwell, right, and then you've got applications here. And so they all kind of track, and you can see here you've got plastics down here at relatively low hardness, and then steels, machinable steels, cutting tools, right, go up in hardness as you go up the scale. And so there's this loose, there's a general relationship between hardness testing and tensile testing, which makes it convenient because you can get very much similar data from a hardness test that you would get from a much more intensive tensile testing. And here's just an overview. So we have, again, just a difference generally in the shape of the indentation. And then that also dictates, right, how you go from the indentation size and depth, or the characteristics of the indentation itself, to the hardness, right? Because what you're doing is you're applying a load to the indenter, and then I'm looking at, okay, what kind of an indentation did it make? Okay, so almost done here. The last thing that I'll mention, and one of the last things that Callister talks about, is the variability. So mechanical testing is very much a statistical business. If you make one measurement and think that you've characterized the material completely, you're wrong. What we're really interested in is the average mechanical properties. So, any one sample, even if you cut 10 identical samples from the same piece of material, right, you're going to get 10 slightly different measurements. And so when you report these values, right, there's always going to be a little bit of scatter in your data. And so what you report is the mean and the standard deviation generally. And so that gives you, and you might see on here error bars, and generally what you're looking at is you would have the center of your data point, say, at the average, and then you would have an error bar that shows that average plus and minus one standard deviation, which gives you a sense for where most of the measurements fall, and how tightly grouped they are, how much variability there is across that sample set. And so because you have this variability, right, because even under carefully controlled conditions, the samples still vary, right, somewhat, and in an industrial sense, you would think that even more so, because you have less control over the conditions in general, that would make it more difficult to engineer with these values. And you say, well, I don't really even know what the properties are, and so partially to deal with that, right, is typically in design that you have the integration of safety factors, right? So I would say, okay, so the average mechanical properties, it might be, I don't pick a number, 50 gigapascals. Or no, that would be, I guess maybe 100 megapascals, right? That would be too high. That would be more like a Young's modulus. Say I have a yield stress of 100 megapascals, and so to be safe, to account for any variability or damage or manufacturing defects, right, I'm going to say, I'm going to apply a factor of safety, right? So this would be some factor that I'm going to divide my yield strength by, and that becomes essentially my working yield strength, right? So if I say that, accounting for all the variance in mechanical properties and reductions that might be due to damage or wear or corrosion or mechanical defects, I'm going to say, accounting for all of that, right, I'm going to apply a factor of safety, say, of 2. Right? So that means that I'm actually going to design for a yield strength that's only half of what I measure it to be. Right? And that gives me some insurance about any variability in these mechanical properties. Now, you can pick a factor of safety that is more conservative depending upon your application. Right? So if you're building a building, maybe you can pick a factor of safety of 4. Right? If you're building an airplane, right, it's more weight sensitive. So generally, the problem becomes harder. You can't pick up a factor of safety that's much above, say, 1.5. And so you are more on the edge from a safety's perspective, right? So you're going to have more inspections. You're going to have more maintenance, more replacement of parts due to age or wear, because you don't have as much of a cushion when it comes to your mechanical properties than you might if your application is large and stationary and you can make it 4 times stronger than it needs to be. Okay, so that's it for mechanical properties. Right? Tomorrow, the chapter is on dislocation motion. And so we'll get a little bit of insight into what is actually happening at an atomic level or at a microstructure level during plastic deformation.